My name is Ross, and we're going to be covering a topic under the biological component for your psychology syllabus under A levels. This study is by Canli et al. 2000. It's to do with amygdala activation and memory and emotions and stuff like that. Personally, I'm not a huge fan of the biological studies. I think they're a little bit on the technical side of things, but I'll try to briefly explain and give you an overview of what this study is about. All right. So first of all, let's do a quick exercise. Now I'm going to show you some pictures, and I want you to rate for yourselves your emotional intensity. How intense are these pictures? From 0, not intense, all the way up to 3, very intense. Or perhaps in the middle, slightly with 1 and moderately with 2. Now it's up to you. You can put this on paper. You can just keep it in mind. It's just a simple exercise. This is kind of simulating what the participants in the study went through. Now a quick trigger warning. There might be some pictures here which may make you feel a little bit afraid or intense in some way. Just letting you know. If you want to skip, you can skip by the next few seconds. But if not, do try and do this exercise just to get a feel of how the procedure of the actual study was, right? So it started up, trigger warning. There's not very intense pictures, just some of them might be a little bit maybe on the slightly disgusting or side. I'm just trying to create an intense emotion, but it's nothing too serious, right? Okay, so this picture. All right, now look at this fixation cross. This is known as a fixation cross, and as you're looking at it, you can perhaps keep in mind how much you would rate the emotional intensity of that previous picture, right? Okay, once again, look at the cross in the middle and rate your intensity. Okay, once again, rate your intensity. All right, so that's basically it. Oh, the last picture was me, by the way. It's crouching in front of the Petronas Twin Towers in Malaysia. It's a beautiful monument. Used to be the tallest twin towers in the world. All right, still is the tallest twin tower, not tallest twin towers, right? Not the single tallest tower. That's the Burj Khalifa right now. So anyway, those were some pictures. Some of them may have been more intense for some of you. Some of them may have been less intense for some of you. And we might we'll use that as a quick discussion with regards to the procedure of this study. So I usually ask my students to tell me what they know about the study. I usually ask them to do a little bit of homework, read up about the study so that you guys are more aware about it. It really helps your learning, right? If you know what you're studying, you can think about this for yourself. We're looking at event-related activation in the human amygdala associates with later memory for individual emotional experience. Canli et al. Yeah? This is a pretty complicated title for something. Biological studies tend to be, as I said earlier, a little bit complex. I'm not a fan of biological studies. I think they're quite full of, a lot of biological jargon as well, and makes the study sometimes a little bit difficult to read, especially the technical aspects. A-levels doesn't require you to really know the ins and outs of human biology that much, right? But you should understand the study in its essence, right? So I'm going to try and break it down in simpler terms. Okay, so we're basically focusing on this part of the brain called the amygdala, the amygdala, as well as memory, okay, and emotion, right? So all three things: amygdala, memory, emotion. Okay, so some definitions first of all. We're going to be looking at this word valence, right? Valence. I call it valence, right? Valence of a particular image, right? It can be the attractiveness, which is positive valence, or aversiveness, which is negative valence, right? Of an event, object, or situation. Okay. Arousal, on the other hand, is the intensity of a stimulus, right? So attractiveness, positive or negative, valence. Arousal is how intense a stimulus is, right? They're very similar words, but let's try to differentiate between them. What's the difference, right? If you're trying to explain it to someone. I find it easier using examples of pictures. So earlier on, I showed you this picture of a crying child, right? And I'm also going to put another picture next to it, right? The picture of the shark. So in terms of valence, right, these pictures would have a negative connotation, right? In terms of this shark may be scary, so you might think that's negative. The crying child, that's sad, so you might think that's negative. So in terms of it's aversive, right? We don't like things which are sad, we don't like things which are scary, and so we're averse towards it. Therefore, we give it a negative valence. But in terms of arousal, are they the same arousal? What do you think? Is one more intense than the other? Is one more arousing than the other? Well, for me personally, I think the crying child, for me, would be more arousing, right? I'd be more saddened, or I would think that's more intense. But for other people, the shark, especially if you're scared of sharks or scared of open water, you might think that picture is more intense. Perhaps you had a bad accident with a shark. So intensity can vary, but in terms of the negative or positivity of this image, we would usually say that both these images are negative. But to what extent they arouse people and how intense they are, that might be different, right? Let's look at another way of looking at it, right? So now the valence is positive, and I want to know the arousal. Again, which one's more arousing rather? Is it the smiling woman, or is it, skydiving? I would say the skydiving is probably really more arousing, right? It's far more intense in activity compared to just looking at someone who's smiling, right? But both are positive, right? Adrenaline rush junkies from, the skydiving side, and also looking at someone who's smiling very beautifully, right? Positive kind of feeling, very attractive. But arousal can be different, right? Some might be more intense, some might be less intense. What if I switch it around? Now the arousal is intense, right? So it's skydiving and the shark, both of them pretty intense images. But what about the valence this time? Would you say that they're both positive or they're both negative? Well, most likely the shark would probably be on the negative side, while the skydivers might probably be on the positive side, right? Something more exciting, more fun. Okay, another definition we need to look at is pixel and voxel. So a voxel is known as a 3D pixel. So you can see from the image, right? On the left side, the pixel is just 2D image. You got your two sides basically, and then voxel is three sides to it, right? Height, width, length, right? So essentially that's basically it. It's like a pixel, but it's in 3 dimensions. Okay. PET, positron emission tomography. fMRI, functional magnetic resonance imaging, and CT, computerized tomography, So these are 3 words that you might come across in the study, whereby they talk about different types of brain scans. These are all types of brain scans. Have any of you done a brain scan like this? I've done an MRI. I haven't done an fMRI. I've done an MRI on my brain. I had a rare condition called palatal myoclonus. If anybody has that, let me know in the comments below. It's quite a rare condition. Thankfully, not too lethal. So I'm fine, but something interesting. Anyway, so types of scans. Broadly speaking, although there are many different names of scans, they functionally differ in these 2 broad categories. Either they're structural or they're functional. So structural scans take detailed images of the brain, basically the structure of the brain, right? And examples would be the CT scan or CAT scan as it's sometimes called, or an MRI, right? It's structure, how the brain looks like. Whereas functional scans show you the activity levels in the brain, right? How the brain functions, how the brain is functioning. PET scans, a good example, or fMRI, right? So don't get confused. MRI is structural, fMRI is functional. The F there stands for functional MRI. Now, look at these 3 pictures. Can anybody guess? Picture number 1, what kind of scan is that? What kind of scan is it? Can you identify from the 3 scans that I mentioned earlier? This is the CT scan. As I said earlier, the CT scan is used for structural imaging. As you can see, the picture is pretty basic, right? Just shows you the structure of the brain, right? The second one is the PET scan, right? And the third one is the fMRI, right? So you can see in the PET and fMRI, there's a lot of colors going on there. And so what they do is they overlay these colors into areas of the brain that are showing activity. Now, we're going to be focusing primarily on the fMRI, right, for this particular study. It uses strong magnetic fields that spins hydrogen nuclei in our brain. It helps us measure brain activity by looking at the changes in blood flow, right? So when you process a visual stimulus, for example, earlier I asked you to look at a bunch of pictures. What happened when you were looking at those pictures? That blood was actually going to your occipital lobe, which controls your vision, right? So the scan can detect this change in blood flow. Okay, it's specifically looking at oxygenated blood, right, and the property of hemoglobin in our blood. when the blood is more oxygenated and there's more blood flowing there, there's a stronger signal. We can see that signal, right? And it usually does a comparison between your brain functions at rest versus during activity, right? So the rest is sort of like a baseline, and during activity is when it's activated by something, right? Okay, so that's pretty much it, quite basic. If there's a change between rest and activity, then people infer that this is an area of the brain that's active, right? That's basically it, right? So if there's a difference from your baseline score, it increases to something else, then you can say that, oh, okay, something's happening in the brain. There's some activity going on there, right? However, I should make a caveat or disclaimer here that in spite of all our advancements in medical scanning technology, we are not always sure, necessarily so, whether or not we're measuring the right things all the time. There is some level of error. In fact, you can find some YouTube videos or some articles online about researchers who put a dead fish into an MRI machine, and it produced brainwave signals that looked as if it was alive, as if it was a human being. So that kind of shows you that there are still errors. We still don't fully understand how to measure the human brain, but at the moment, these are the best scans that we have available, right? Okay, so that's the structure of the human brain. The amygdala is highlighted in green there. It controls our emotions and also our memory, right? The hippocampus as well for memory, and the amygdala today we're going to be looking at how it enhances memory, right? Now, that part over there, right? And there are actually two halves, or rather two sides, not two halves, but two sides to the amygdala. As you can see there, it's a small little yellow color thing at the end of the blue, sort of like flange, I don't know what you would call that, the hippocampus, right? At the end of the hippocampus, there are two pieces there, the right side and the left side. So there's a right and left amygdala, right? They're similar, but they differ slightly. And we're going to look at the differences slightly, perhaps later in our slides, right? There is a slight difference between them. Right. Is it beneficial for the brain to have certain areas specialized for certain tasks? So if you're familiar with the structure of the brain, there's the occipital lobe that handles vision, and all the the frontal lobe that handles thinking and stuff like that, and parietal lobe and all the other lobes as well. Now, each of these lobes, each of these sections of the brain seem to be specialized for certain function, right? For vision, for thinking, for motor, neuron activity, whatever. So is it beneficial for the brain to be like this? Well, some people say yes, because, why would it be a benefit? If everything's specialized and perhaps one area gets damaged, then in that sense, the other areas are still able to function, right? So there's a damage to your occipital lobe, you may lose your vision, but your frontal lobe can still think and all that, and your other lobes are functioning as well, so you can still move around, but perhaps you may just lose your vision, right? However, on the other hand, you might say that it's not necessarily beneficial, right? It would be better if the whole brain was doing everything together simultaneously. Why? Because then you can perhaps share the neural workload, right? Now, I like to use the example of Pacific Rim. If you remember Pacific Rim, two pilots share the neural load of the Jaeger, right? So this is kind of like if everybody's brains, all the lobes will sort of like just combine into one, right? Then the neural load might be shared, it might be easier, we might be able to do things better. Who knows, right? So this is something interesting to think about. Right? Let's look at this very famous example of Phineas Gage, right? One of the most famous examples in psychology. This guy, Phineas Gage, who survived an accident where a steel bar went right through his skull. He survived, right? He was alive. However, his personality did change a little bit, right? He was a bit colder, if I remember correctly, after his accident. He recovered. He's still alive, but things changed, right? He changed slightly, right? So that's interesting that even all this incredible brain trauma, he was still able to function, perhaps only because the fact that different parts of his brain were able to pick up the load and still continue functioning as per normal, right? Almost as per normal. Right, so let's look at some past studies. Christensen, 1992, Labar and Phelps in 1998. They found that emotional experiences are better recalled, right? You've probably noticed this yourself, right? You've gone through a very emotional time in your life. Perhaps you won a competition in your school, right? And that was the proudest moment of your young life, and you're like, oh man, I'll never forget this, right? So those are important moments you remember, especially the emotional ones, right? A strong emotion attached to it. And mundane things like what you ate for breakfast today, you probably don't remember, right? But if it's particularly emotional for you, right? If today was your birthday and your friends came over and surprised you for breakfast, yeah, that would be something that you might probably remember more, right? What else? That was by Christensen. And emotional arousal it was almost equal to better memory consolidation or storage, right? Now, this was by Labar and Phelps. They added this in. They agreed with the first statement, that emotional experiences are better recalled, but they also added to it by saying that there's better memory consolidation. So the storage, right? When our emotions are activated, our storage is better. We're able to store the memories far better than if they had been just mundane memories, right? Or no emotional arousal, rather. Cahill et al. In 1995 and adults in 1997, they found that people remember emotionally vivid stories rather than the neutral parts of those stories, right? So if there was a part of the story that was emotionally vivid, you'd probably remember it more, right? For example, if you take the simple story of Little Red Riding Hood, most of you probably wouldn't really remember what happened in the beginning of the story. It's kind of boring. She's just walking around the forest with a basket, but you probably remember the part where the wolf suddenly comes in and tries to attack, right? So that's the story of Little Red Riding Hood, right? You probably remember the vivid parts in more detail, whereas the neutral parts you may kind of forget, right? Think of the stories that you know, right? Which parts do you remember more, right? Now, people who had bilateral amygdala damage don't seem to remember the vivid parts better, that is, right? So that if there's some kind of damage to the amygdala, they found that, they don't seem to remember the vivid parts as well, right? So there seems to be some connection here between the amygdala and this memory of vivid parts of the story, right? Another few studies, they looked at PET scans and fMRI scans. They found significant correlations, right, between amygdala activation to do with emotions and also memory, right? So previous scans have found some evidence for this. No correlations, however, when exposed to neutral stimuli, right? So when you see a neutral stimuli, the correlation between amygdala activation and memory doesn't seem to hold up anymore. It only happens when they're seeing something particularly emotional. It's particularly emotional, and those who saw something particularly emotional had superior memory, right? Superior memory for said stimuli as compared to neutral stimuli. Right? Now, there are some weaknesses that were highlighted regarding past studies. Firstly, let's look at this one. Many brain scan studies in the past used a between subjects design. Okay, anybody remember? What are the weaknesses of the between subjects design? So if it's between subjects, it means that everybody just goes through one level. And the problem here is that if everybody just goes through one level, then there are a lot of individual differences, right? A lot of individual differences. And some individuals might be more responsive to emotional experiences than others, right? So therefore, if you think about it that way, the activation would reflect something about their personality or their, something that's individual to them, rather than that something is coming from the IV, right? That's being manipulated. So that's one of the weaknesses of a between subjects design, right? There's more individual differences. The second would be that this weakness can lead to three different explanations. First of all, as I mentioned earlier, one could be that the activation in the amygdala might be a result of what is like a personality characteristic, right? Or perhaps the second reason that the person might be, during the scanning session in a state of enhanced responsiveness, meaning that, they might be, perhaps not everybody who goes into an fMRI machine would be okay with it. Some of them might feel a bit scared, some might feel worried, that obviously is going to trigger them, their amygdala is going to be perhaps more activated, or some of them might be perfectly comfortable with it. So yeah, it's a bit hard to say. I don't know, if you were in a fMRI machine, it's making boom, 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 all those big sounds, how would you feel, right? All right, so let's just recap. Individual differences, enhanced responsiveness, and the third reason might be that the amygdala is dynamic, right? Dynamic. So how should I explain this, right? Well, so the thing here is amygdala activation may be rapid. It's a bit of a tricky point to explain. In a sense, we're saying that the amygdala activation should be changing from moment to moment, right? It's dynamic in the sense that it doesn't stay the same way for everything. Now, as we saw earlier in the studies, there's some evidence for this, whereby when you look at a neutral image, for some reason, the studies don't pick up much differences in the amygdala activation as compared to when you look at something that's vivid, right? There seems to be a lot more differences there. And so that's interesting, right? That's interesting for us to know, because that shows that there's some kind of dynamicness to the amygdala that is not just activating in a necessarily consistent way. It's almost like it's selective, right? So it changes from moment to moment. It's flexible in a sense, right? Well, these are some of the things that we want to look at, right? We want to control for those problems, and we also want to look at whether or not it's truly dynamic or is it static, in a sense, right? And one of the issues that the between subjects design doesn't really allow us to look at this because the individual differences are very high. So we're not sure if it's the differences in the IV are being caused by the individual, or is it being caused by the amygdala, or is it being caused by the stimuli, right? We don't know for sure whether what is affecting our results, so we need to change the design. Now, how do we solve it? Well, we could use the other kind of design which we are familiar with, which is the within subjects design. Now, if the amygdala is dynamic, then it should be sensitive to emotionally intense stimuli, right? If it is dynamic. So previously, there is some evidence that shows that neutral parts of a story doesn't seem to activate much. We don't really remember it as well. So there seems to be some evidence to suggest that the amygdala is indeed sensitive to emotionally intense stimuli. And that's what we want to find out in this study, right? So let's look at the aims. First of all, we want to study if the amygdala is sensitive to varying degrees of individually experienced emotional sensitivity, right? Can the amygdala tell the difference, or does it change? Does it change in its sensitivity towards stimuli that's emotional, not so emotional, and stuff like that, right? Can it detect these degrees of emotional sensitivity, right? Next, the degree of emotional intensity affects the role of the amygdala in enhancing memory for external stimuli. So firstly, we want to see whether the amygdala can differentiate, right, between the levels of emotional intensity. And once we've established that, then we can look at whether or not the emotional intensity affects the amygdala's role in enhancing memory, right? Does it indeed enhance our memory or not? Right, so we'll look at that in this particular study. Let's look quickly at the method and design. So it was a laboratory experiment. Now think about the strengths and weaknesses, right? You definitely have a lot more control over the variables, which is important, right? You want to try and determine a causal relationship as much as possible between your independent variable and your dependent variable by reducing possible extraneous variables. Weakness, however, naturally would be things like, the fact that they're not in a natural environment, right? Participants are being brought into an artificial environment with an fMRI machine. Their behavior might be different. You never know. They might, not like the environment. They may not behave in the same way, right? Also, it's using a repeated measures design. Now, repeated measures design does overcome some of the weaknesses that we identified with the individual differences problem in the between subjects design. Of course, there is a strength. It reduces individual differences because fewer participants are needed and each person goes through the same condition. The second condition of the IV, right? The IV has 2 levels. Each person goes through all levels of the IV. That way you can compare them against themselves, right? So you eliminate this issue of individual differences. However, the issue would be the weakness, would be that there are possible order effects and also more demand characteristics because everybody's going through the levels of the IV, right? So they may figure out the aim, or they may get better at it, or they may get fatigued, different things like that. Let's look at this study as well. Okay, so the IV in this study is intensity of emotional arousal, measured using, manipulated using 96 different scenes. With a scale from 0, not emotionally intense, to 3, extremely emotionally intense. So this is similar to what I did in the exercise earlier. Showed you a bunch of pictures. Of course, I showed you a few. Here you have 96, right? 0 to 3 is the rating. The DV1 is the level of amygdala activation. You want to see whether the amygdala can differentiate, right, between these emotionally intense pictures, measured using an fMRI. Each scene had 11 fMRI measures of neural activity. Okay, we'll look at that in a moment, right? But each scene had 11 corresponding measures. Okay, we also had a second DV, which is memory. Now, the memory was either a person could list out that they had either forgotten the picture, they were familiar but not very sure, or they definitely remembered that picture, right? They were sure of it, right? So 3 different levels of memory recall, right? The sample were 10 people, very small study, right? Only females, and they were all right-handed, right? Why were they only females, right? If you read the study, can you just think of a reason why? If you haven't read the study, why do you think only females were used in this study? Hint, hint about, emotional stuff. I'm not trying to be sexist here, but women were chosen in the study because, according to research, they are more likely to report intense emotional experiences. Okay, you can see that citation by Shields 1991. It's available inside the study. And also, women tend to show more physiological reactivity, right, to do with valence judgments as compared to men. Also, that was by Lang et al. 1993. You can check out those citations. So again, we're not trying to be sexist here. We're trying to use research to inform us of what we should be doing. And the researchers decided that because females tend to be more willing to report their emotional experiences more, as well as are more physiologically reactive to emotional experiences, they decided to recruit females instead of males, right? And that would be helpful for the study because then they get people who are willing to, talk about their emotions or rate their emotions more accurately, perhaps, right? So that's good. Now, this is not to say that men don't experience emotions. Men do definitely experience emotions, but perhaps at a different level of intensity, or perhaps they may not want to share their emotions as readily as women do, right? Okay, also you'll notice that they're all right-handed. Now, why do you think that might be? That's an interesting point, right? That why are they all right-handed? And that's a specific point that was listed in the study. Well, I'll give you a little hint, and you can perhaps do some research on this on your own. If you think about it, the brain is actually cross-wired to our body, right? So the right hemisphere controls the left side of the body, while the left hemisphere of the brain controls the right side of the body. So if someone who is a right-handed participates in my experiment, that means that their left amygdala is probably going to be more active, right? Because they're right-handed, so everything they control on the right side means that the left side of the hemisphere of the brain tends to be more active, right? So that's just a little hint that I'm going to give you. As I said earlier, the amygdala has two sides, the left side and the right side. For this study, we're going to specifically look at the left side of the amygdala because we have right-handed participants. Now, you can probably look in the study and find out a few more details why that is the case. Okay. Oh, I just put this joke in to make my students laugh, and why do they all use women? Well, women keep laughing and whenever the salad makes jokes. That's why they're, willing to show their emotions, right? If you go online and look for a picture of salad, you'll always find a very happy, laughing woman next to it, right? It's kind of funny. All right. So who is more emotional? I asked my students to decide who's more emotional, men or women. Both genders are equally emotional. It's just sometimes, one particular gender may be more comfortable expressing their emotions than the other. Right? Materials in this study. So first and foremost, the most important, of course, is the fMRI. Now, you can look up in the study and memorize if you want to what it's fully called, right? It's a 1.5 T or Tesla. The T stands for Tesla. A 1.5 Tesla General Electric Sigma MR imager, right? So this is used to measure the blood oxygen level dependent, or the bold contrast, as it's called, blood oxygen level dependent bold contrast in the brain, right? Remember, again, it's looking at the blood flow. Whereas the blood flowing more, that usually indicates which part of the brain is more active, right? Okay, so some complex stuff. This is one of the things I really dislike about biological studies. A lot of complex terminology to get past. So I'm going to make it a bit easier. I'm just going to remove all of that with a black color box, and I'm just going to ask you to focus on what I think is important. First and foremost, the head movement of every participant was minimized using a bite bar formed with each subject's dental impression. Right? So what's this? Basically, it's a form of standardization in the procedure. Also, you could tie it into validity. Why? Because you see, what happens is when people move, if they're in the fMRI and they move their head too much, these scans will not be accurate. If you've ever done an MRI scan before, you need to stay absolutely still. And even then, there's still going to be some issues with movement, so the computer is correct for that. But as much as possible, they wanted people to remain still, and so they had a bite bar, right? They bite on something, and they had the dental impression. That's pretty impressive, right? So to make them really feel secure and not move as much as possible. And if you look at the next point, there's something called the motion artifact. Now that word artifact, A-R-T-I-F-A-C-T, refers to something in scientific studies whereby the issue is that a variable is occurring or affecting your results due to the way that the experiment is designed, right? It's not coming from IV, it's coming by something from the procedure or something like that, right? It's not an effect that is part of what you're manipulating, is an effect that's part of simply the way that you run the experiment. I'm assuming that the motion artifact, so something that's regarding motion, is when the fMRI machine moves in and out, there's probably going to be some vibrations there, some movement, maybe someone sneezed or something, right? So that was corrected for automatically for all scans using something called AIR 3.0. right? Now, the earlier parts which I blacked out are basically, technical information about the angles and stuff like that, how many millimeters and stuff like that. While I think in A levels they can ask you questions about it, I highly doubt they will, and if they do, that would be quite painful to students and examiners alike because it's really technical information. I tend to highlight what I think is really important for exams for my students. And this is my personal opinion. You don't have to listen to it necessarily. If you want to memorize all the other technical info, feel free to do so. There's no problem with that. Right? Now, they use the word slices, right? They do brain slices. Now, what does this slices mean, right? So, as I said earlier, it was measured 11 frames were captured per individual trial, right? 11 frames. And there was a baseline fixation of frame 1, 2, 10, and 11, and also an activation from frames 5 to frames 8. Now, baseline fixation, activation period. Do just keep this in mind because it's important for us to realize that not all 11 slices were when the brain was active. Some of them were considered a baseline. Right? What do I mean by that? So this is a simple example of what the brain scan might look like in terms of slices. Again, this is not an actual fMRI scan. This is an MRI, not an fMRI, an MRI. Right? This is more towards structure. You can see the picture of the brain. So it starts from the top left-hand corner and goes all the way to the right. You can see it's getting bigger, right? Because it's going through your brain structurally and seeing everything that's inside and your skull and all that. I did something like this when I was younger. And but that's basically showing you, right? So there are different kinds of slices there. I couldn't find a picture of fMRI slices, but this just as a visual example of what the slices might look like, something along those lines, right? So the question here we need to ask is, why is it 1, 2, 10, and 11 are considered baseline? Why are they considered baseline, even though they're all being done on the same person at the same, during the same experiment? Well, the reason why is because there's an approximately 4-second period in which, after the presentation of a stimulus, there's a slight lag in the response of the brain, right? In terms of how our thoughts may be going faster, but the blood rushing there may take about approximately 4 seconds before the blood is going there and showing us the activity, right, on the scan, right? Of course, thinking is a lot faster, right? Within milliseconds, nanoseconds, we can think certain thoughts and all that. But when our blood needs to go there, it takes a few seconds to get there. And so imagine you show them the stimulus and then scan number 1, scan number 2, the blood hasn't reached there yet. After about 4 seconds, it's gone there. So that's about scan number 5. That's when they start taking those scans as the activation period. And then after your brain has been activated, it slowly dies down, the response dies down. And towards the last 2 scans, scan 10, scan 11, the brain should be going back to a resting state, right? So again, another baseline. Okay, how is the image formed? Well, it looks something like this. This is a picture taken from the article itself. How is that formed? Well, let's look at it. This is really complicated. If you don't understand it, let me just explain it the simplest way I can possibly think of. Of course, simple doesn't necessarily mean most accurate, but it's a simplified way of explaining it. They take the voxels, and remember, voxels are 3D pixels. So they take the 3D pixels from the activation scan minus the pixels from the baseline scan, right? So they're taking the activation part, they're minusing the baseline part, and what's left should be the parts of the brain that light up to show activity, right? So again, something like this. So the activation scans will scan 5, 6, 7, 8 minus the baseline scan, scan 1, 2, 10, and 11, right? And they should get something like that. Again, these are just examples. These are not exactly how it's done. These are just simplified ways of understanding how the brain scan was put together. Okay, very simplified ways, right? They used an average structural image, right? So the image, the shape of the brain, that's the structural part, right? They used the average structural image for all the participants, and then they took the significant voxels or 3D pixels for each participant's activation, and they averaged it out across all their scans, right? And then they averaged that across all the different participants, right? So they took the average of each participant, then they averaged it across all the participants, right? For each trial, right? And then the significant voxels or the 3D pixels that were left were colored and overlaid onto the structural image, right? So the pixel there highlighted in the green circle, that's the activation of the amygdala, right? The left side amygdala, as you can see, right? And then the structural image is the whole shape of the brain, right, around it. Okay, so basically this is an average of everybody's scores, right? Now, other materials were the pictures, as I mentioned earlier, 96 scenes. They came from the International Effective Picture System, IAPS system, right? The normative valence ranged from 1.17, highly negative, to 5.44, right? Neutral. The normative arousal, right, was from 1.97, tranquil, to 7.63, highly arousing. Tranquil is a fancy word for peaceful, or not basically the opposite of arousing, right? Something that's peaceful and not too arousing, right? Again, so these were the system of pictures. I actually wanted to get a sample of some of the pictures to show you guys and show my class as well, but unfortunately I emailed the IAPS admin, and they said that it's not allowed for classroom usage. It's only used for research. So if you're a researcher, then you can ask them for a copy of the pictures, and then you can use that in research, right? But you can't just use it if you're showing it to students, which is a pity. You know, I would love for them to see what the actual images were. Okay, what does normative mean, right? I use the word normative valence and normative arousal. What does normative mean? This refers to the norms or the standards, as the word norm in normative suggests, normal or standard, right? Basically, the pictures in the IPS have been tested around the whole world with hundreds and hundreds, if not thousands and thousands of people, and all the ratings for those pictures have already been established, right? So if there's a picture of a spider, it's been rated on average around thousands of people. This is what the intensity of a spider is on average for human beings, right? This is what the arousal level is of a spider. This is what the valence is of a spider, you know, a picture of a spider that is, right? Around the world for thousands of people, right? So that's the norm that has been set. And so these pictures were chosen with a range of norm from, highly negative to neutral, and highly arousing to neutral, highly negative to neutral, and peaceful to arousing, or tranquil to arousing, right? Yeah. So what's the difference again between valence and arousal? You guys remember? Valence is about the value of something, right? It's positive or negative, value. That's how I remember. V for value. Is it positive or is it negative? Arousal is for your intensity. You know, how intense something is, right? So this is an example that I could get from online. So I got it from Science Direct. It's the ISEE, which basically is the image stimuli for emotion elicitation. If you look at that, it actually spells out I see, which I think is a funny way that researchers show their sense of humor in the real world. Not all researchers have a sense of humor, but anyway, it's fun to see things like that. I only realized it when I put these slides together and I'm like, oh my gosh, it says I see. And indeed, we do see the pictures there. As you can see, there's a difference between valence, arousal, likability. So they've got our likability here. Again, these are not the pictures that were used in the actual study, which is from the IAPS. This is a different system, right? But you can see there, right? High effect on the left, the arrow there, and then neutral effect and then low effect. Valence and arousal, right? So those are the kind of pictures there. You can see some pictures of, skies, some pictures of people, some pictures of colorful stuff and all that. And so, all sorts of different pictures are there, and these have been rated, right, according to the IC. Okay, let's look at the procedure. So what was the procedure like? Informed consent, but was it full? Well, this is interesting. We're going to come back to this point. If you read the study, you would know the answer. They did have informed consent probably, but was it full informed consent? Let's think about that later. They went into the fMRI machine. They viewed 96 different images or scenes, right, using overhead projector and a mirror, so they could see inside the scanner. Right, they viewed each image for 2.88 seconds. I'm not sure why that specific number. Why wasn't it just 3 seconds or 2 seconds? No idea why. But 2.88 is the exact number given in the study, so please memorize that. Each picture for about 2.88 seconds. And also the fixation cross, which was just a cross in the middle of the screen, was viewed for 12.96 seconds. Now, again, I'm just giving you an example of a white cross in the inside of a black box. That may not necessarily have been the exact fixation cross. I don't know what the exact fixation cross looked like, but that's basically what it was, a cross in the middle of a blank space, right? So just do take note of memorizing those specific numbers. Yeah. Again, I don't know why it wasn't just 13 seconds or 12 seconds. Why was it 12.96? So specific, I'm not entirely sure why. Okay, to indicate the emotional arousal, after they had seen an image, they would press one of 4 buttons during the fixation cross period. Right? So during that 12.96 seconds, they can press one of those 4 buttons, 0 to 3, remember? Either not in, before I go there, I should go back here. Okay. Supposed to do the voice. Let me go back to this again. Right, so they could view the images, and then during the fixation cross point, they had to press one of 4 buttons. Again, the 4 buttons are 0, 1, 2, 3. 0 being not emotionally tense at all, and then 3 being extremely emotionally intense, right? And then 3 weeks later, okay, and that was a complete failure. 3 weeks later, I don't know how that guy on SpongeBob SquarePants does his voice, but yeah, anyway, I got this from SpongeBob SquarePants. It's become a meme whenever you want to show the interval of time. Okay, procedure. The procedure was an unexpected memory test suddenly, right? After 3 weeks, they had an unexpected memory test, and that's why I said the informed consent wasn't necessarily full, simply because they were not informed of this unexpected test, right? What else? They viewed the 96 scenes again, but this time there were 48 foils, right, which had matched levels of valence and arousal, right? And there was no significant difference between the foils, and the 96 scenes. in terms of their normative valence and also their arousal ratings, right? There was no significant difference. All of them were similar. All of them were similar, right? Excuse me, having a bit of issue with my microphone. It's making some sound. Okay, it's back there again. Fix that a bit. All right. So the normative valence for these foils was 1.31, highly negative, to 5.78, highly neutral. Normative arousal was 2.74, tranquil, to 7.22, highly arousing. Again, these are for the foils, and they were comparable to the 96 scenes, and there was no significant difference, right? Which is why they were usable, right? Because there was no difference in them. Okay. Now, they were asked to judge these scenes as well, all of them, right? 96 plus 48. And they also asked to tell the researchers if they had seen them before. Now, they could have said, no, I don't think so, so forgotten. Or yes, if you think you have seen it before, how sure are you? Right? Or perhaps you're not so sure, then it is familiar, but you're not very sure. Right? So either they're forgotten, sure of it, or not so sure. Right? And very sure. Very sure means they are remembered. Right? So if they had said no, then that means they probably forgot if it was one of the 96. If they had said yes to any of the 96, then they would be asked a follow-up question, how sure are you? Not so sure? Familiar, a little bit. Or very sure, I definitely remember seeing this, right? So then it's remembered, right? And they wanted to use that to judge their memory. Okay, let's look at the results. Participants and their normative ratings. Okay, so were participants' scores of emotional intensity correlated with normative ratings, right? Let's look at that. Emotional intensity and normative valence. Now, emotional intensity is what they rated on the button, right? They pressed the button 0 to 3, how emotionally intense they found a particular image. Now, I'm going to compare that with the normative valence of the image, right? Now, remember, this normative valence is what has been tested in the IAPS amongst thousands of people. That's what the norm is, the standardized norm value given to that image. And want to see whether or not our participants in the experiment, do they have similar values, right? Are they correlated to the norm? And the answer is yes, indeed they are, right? Negative 0.66, so it's a moderate level comparison, a moderate level correlation, okay? And emotional intensity was also correlated to the arousal, right? In the normative values, there are two: valence, which is the value positive or negative, and arousal, which is how intense something is. They want to see in comparison to the standardized value, what was the result? The result was very similar, yeah? Positive 0.68, very similar to the other one, 0.66, 0.68. Now, a question here for you guys to think about is, why is one negative and why is one positive? Wouldn't we want them both to be positive? What do you think? Okay, if you remember about correlation, right, the hint here is correlation can have negative and positive values. Now, if we look at the first one, the negative 0.66, right, that is negative, and therefore it basically means that if one variable goes up, the other variable goes down, right, opposite direction. That's what it means. Now, in this sense, emotional intensity, right, so if something is intense, and then because remember we looked at the valence scores are all mostly negative to neutral, right? Mostly negative to neutral. There are no positively valenced items in this particular study. They only use negatively valenced items, right? So we can assume that here the negative correlation here is basically saying the more intense something was, the more negative the valence was, right? In opposite direction. Right, and with regards to the second one, 0.68, right, it's positive. So the more intense something is, the more arousing it was, right? So this kind of followed the expectations that we had, right? If we expect something to be very highly arousing, we expect it to be intense for my participants, and that showed clearly the exact same result, right? So basically what we're saying here is subjects' ratings of emotional intensity, right, reflected what the norm standards were for the valence and arousal for the IAPS images, right, for the stimuli, right? So that's good. That shows that our participants are rating the stimuli as they were normally rated in the IAPS itself, right? So let's look at now a graph representing the amygdala activation and emotional intensity. Remember, we want to see whether or not the amygdala activates, right, in the presence of emotionally intense stimuli, right? So amygdala activation was indeed significantly correlated with higher ratings of emotional intensity. If something is more emotionally intense, the amygdala activation was indeed higher. What can you interpret from this graph? So let's look at the top there, right at the top there. I've circled it in red. If you look at the green line is rating 3. That means these are items which received a rating of extremely emotionally intense, right? It goes up all the way there at scan number approximately 7, right? Scan number 7. So that's right in the middle of the activation period. The amygdala activation was extremely high. Highest percentage of activation was for the emotionally intense scenes, right? So that basically follows what we what we hypothesized. If the more intense that they are, the more the amygdala activation would be, right? And right at the bottom one, you look at the bottom one now, that was given a rating of 0, right? So these are not emotionally intense pictures. Let's say a picture of the sky, for example. So right around 7 to 8, around 8 there, scan number 8, you can see the activation is very much lower, right? Interestingly enough, you look at scan number 10 and 11, or scan number 1 and 2, you'll see the activation is quite high, right? So that's actually the resting state of that person's amygdala is higher activation. And then when you see the neutral stimulus, it actually brings down the activation, right? So the amygdala activation actually falls when they see something that's neutral. But when they see something that's vivid and emotionally intense, the activation shoots all the way up, really, really high, right? So that's interesting, and it basically confirms what we said earlier, right? The amygdala is indeed significantly higher activation when it encounters emotionally intense images, right? Right? Something I took from the study screenshot, it says this represents first evidence that the amygdala activation is related to the subjective sense of emotional intensity. So how you find something as emotionally intense, that triggers your amygdala activation. Now let's look at emotionally intense ratings, or emotional intensity ratings, right? Similar distribution for all ratings, right? So what we're saying here, went a bit too fast. So we're looking here at the emotional intensity and then the distribution, right? So some images were rated 0, some 1, some 2, some 3, right? That's a scale of the emotional intensity that people could press on the buttons. And it's nice to see that the distribution was almost equal, right? 29% in 0, 22% in 1, 24% in 2, 25% in 3. That means that they're almost similarly distributed, right? Which is good, right? If, for example, that like 70% of the images were rated number 3, that might be a problem for the study, because there are too many, there's too much emotionally intense images going on, right? There's too little of the others to make an accurate comparison. Or if 80% to 90% of the images all fell under, category 0, right? They're not emotionally intense. Then really, what am I measuring, right? I can't really make an accurate comparison with the others. But in this case, they're almost pretty much the same, right? Between 20 to 30%. So that's good. I can make a somewhat a more valid comparison, I think. Yeah, I think I can say that. A more valid comparison between the different levels because they're somewhat similarly distributed. Right? Now, how was their memory performance? We looked at the activation. Now let's see how their memory did. So this is the scale that's given. Let's focus on interpreting this graph. So I'm going to highlight the bottom left-hand corner. I like to look at the highest and the lowest, right? That's usually what I focus on. So these were rated 0, right? These were the images on the extreme left. Those 3 bars are referring to images that had the lowest emotional intensity rating. Let's look at the 3 bars, right? There's a black bar, a blue bar, and a pink color bar. The highest bar is the black bar. What does the black bar represent? It represents forgotten, right? The percentage of people who said that they forgot this image, right? So basically what they're saying is that the images which were not emotionally intense, most of them were forgotten, more than 40%, right? But almost 45% of them were forgotten, these images which were not emotionally intense. Some of them, of course, were remembered, about 30, 32, 33%, and then maybe 21, 22% were somewhat familiar but not sure. But the highest there is the highest percentage of those people basically said that they forgot this particular image, right, when they had given it a low rating. Now remember, these memory scores were taken after 3 weeks from the procedure, right? So naturally you could say that, yeah, people won't always remember 96 different pictures after 3 weeks, right? But let's look at the extreme right side of the graph, rated 3. So these were the images which were extremely emotionally intense, right? Very intense pictures, like let's say something particularly scary, like a big spider and something like that. So very emotionally intense pictures. What's the highest bar there? We can see the complete opposite, right? It is the pink color bar, which shows us the percentage of people who remember these images, right? So let's say a house on fire, right? You would have remembered that image even after 3 weeks. You say, yes, I definitely remember this picture, right? This picture was definitely there the first time. And so that's why the higher percentage, more than 40%, said that they did indeed remember most of these pictures. In fact, quite a high percentage as well said that these pictures seemed familiar to them, right? Even if they were not entirely sure, they were somewhat sure that they had seen these pictures before. And the lowest bar, of course, the black bar, which is the forgotten, right? And most of them did not forget, or rather that's the lowest, right? The lowest percentage is those who said they had forgotten these images, right? So that kind of basically concludes for us that yes, indeed, the more emotionally intense the pictures were, the easier it was for people to remember, right? There seems to be some kind of enhancement in people's memory, right? The more intense they are, the more easily remembered it is, right? So, is this a bar chart? This is going back to our research methodology knowledge about charts, right? Is this a bar chart? Yes or no? Well, yes, it is. It's a special kind of bar chart, right? Which features a combination of three different bar charts. So, actually, if you were to take out the three different colors separately, the black bars could actually form their own bar chart on forgotten. The blue bars could form their own. The pink bars could form their own. And you could actually have three separate bar charts. But what we've done is we've combined them all together in one bar chart, as sort of like a combination bar chart, so we can compare against all of them. Now, the question here is, why not a histogram? Why can't we use a histogram? Why do we use a bar chart instead? Does anybody know why? Well, if you remember your knowledge, right, from research methodology, a bar chart is useful when the categories are discrete, right? When they're different categories from each other, right? And because we're categorizing 0, 1, 2, 3, right? Those are separate categories. They're not continuous. They're not necessarily continuous, right? Because they have a certain order to them, right? In terms of an ordinal kind of a scale, right? They're not necessarily a continuous scale. Sometimes people treat them as continuous, but it's not actually accurate, right? These are all on more of a categorical variable like apple, orange, and stuff like that, right? They're not necessarily on a continuous scale. So a bar chart is preferred. False positive. So what are false positive? This is mentioned in the study. A false positive is a test result that indicates a result which is not there. So you did a test, you found a result, said, yay, I've got a result, this happens. And then actually that result in reality does not exist. You accidentally found a result that does not exist, right? So that's called a false positive. Positive because you reported a result, but false because the result that you reported doesn't actually exist. Sometimes that happens, right? Accidents, error, you might say that something exists when it doesn't exist, okay? So what happened was they measured, right, the false positive for foils, right? So only 10%, right? There was a mean of 10% of people who selected the foils as a actual scene, right? Remember, there was 48 foils that were interspersed to try and confuse participants, but only 10% of them got fooled by the foils and said that, oh, I remember this picture, but it actually wasn't there, right? So very, very low hit rate of false positives, which is a good thing. That means most people in general did not fall for the foils. They knew that these foils, I've never seen this before, this is new, right? But only 10% did, unfortunately, right? Well below the hit rate. And the success rate for scenes, right? The hit rate for 96 scenes range from about 22% to 44%. So that's good. That's showing that people are fairly accurate when it comes to rating the scenes, remembering or not remembering them, whereas the foils are far below that 10%. So it's kind of good in the sense that, it's telling us that participants were able to differentiate between the foils and the actual scenes, and they could differentiate it fairly well, right? Okay, additional analysis was done. A correlation between emotional intensity and the modulatory, modulatory influence of the amygdala on emotional memory, right? So that's a very fancy word there. I'll try to explain it to you. The word modulatory comes from the word modulate, right? To make something, you can think about it this way, right? To make something stronger or weaker, that is a modulator. It modulates, right? Like how your modem modulates the signal, right? So what we're looking at is how this amygdala is able to modulate, right, emotional memory, right? How is it able to increase, decrease the strength and stuff like that? So you look at this graph, right? At the bottom there you see intensity rating again, 0 to 3, so how intense a stimulus is. The average z-score, basically z-score is a standardized way of measuring something, right? And also the number of significant pixels. So we're looking at the pixels activation that's in the brain. The significant pixels show that, there's a higher level of activation in a particular area, right? So the correlation between amygdala activation and subsequent memory grew stronger, as you can see that's going up there, as subjects experience greater emotional intensity. So look at the black line, right? The black line is showing that they're more emotionally intense is increasing, and the number of pixels, significant pixels, are also increasing, right? And a particularly sharp increase from rating number 2 to rating number 3. Right? So what it's basically saying is that it suggests to us, right, that really sharp increase. You can see rate 0, 1, 2, they're kind of similar, but rating number 3 really shoots up really high. What's that indicating? It's basically telling us that a stimulus may need to exceed a certain threshold of emotional intensity before the amygdala activation can produce enhanced memory, right? So unless a picture that you're looking at is really emotionally intense, it doesn't really trigger the memory enhancement that the amygdala can provide, right? If it's just a neutral image, your amygdala doesn't get triggered into enhancing your memory. But if it's a really emotional image, right, very emotionally intense image, your amygdala gets pooped, excuse me, not pooped, kicked into action, right? And then it says, okay, let's enhance this memory, right? So that's basically what it's saying, right? That you need a significantly emotionally stimulating item in order to really kickstart the amygdala's modulatory response, right? So it modulates memory to enhance a person's memory, right? So that's pretty interesting, right? The more emotionally intense something is, the better you are at remembering it. Okay, so right there at the top. Also, we can basically, basically comparing these two graphs is basically telling us the same thing, right? The left side of the graph is kind of like the behavioral measure, whether you remember something or don't, and you report it yourself, right? So that's a self-report kind of a measure, whereas the graph on the right is using more of the scanning, right? So that's more of the objective side of measuring it, and both of them complement each other, right? The more emotional something is, the more you remember it, right? And that's both on the self-report side and also on the pixels side, right? We can see from the significant activity of the pixels. So a stimulus may need to exceed a certain threshold of emotional intensity before amygdala activation is likely to modulate memory to produce enhanced memory for that stimulus. Basically, what I said earlier, took it straight from the study, right? The more intense something is, the more likely your amygdala will modulate your memory to help you remember it better, right? Just imagine yourself, if you're eating breakfast, how much are you likely to remember that activity versus, you just survived a car accident. How likely are you likely to remember that activity, right? Something that's more emotionally intense, your amygdala kicked into action and said, remember this, let me enhance your memory, right? So that's interesting. It seems, it's interesting to note that the amygdala helps our memory, especially for things which are emotionally intense. It's kind of like telling you, this is important, I should remember it. Right? Now, only when the stimulus is intense, the amygdala enhances memory, right? Just to repeat that point. Conclusions, what can we say? Now, conclusions would be that yes, the amygdala is sensitive to individually experienced emotional intensity of a visual stimuli, right? So it is sensitive. We can see that the more emotionally stimulating a particular stimulus is, the more sensitive the amygdala becomes, right? Because it activates more, right? We also saw that activity in the left amygdala during encoding is predictive of subsequent memory. But basically, what we're saying is that amygdala activity predicts memory, right? Particularly in the left amygdala. Remember, again, we're using right-handed participants. We're looking primarily at the left side of the amygdala, the left amygdala, right? So, more amygdala activity seems to predict your memory, right? And the degree to which amygdala activation at encoding can predict subsequent memory is a function of emotional intensity, right? As I said earlier, the more intense a stimuli is, the more enhanced your memory. So going through them again, number one, right? Amygdala is sensitive to emotional intensity, right? The more emotionally intense something is, the more your amygdala activates. And the activity in the amygdala seems to predict subsequent memory, right? And last but not the least, the function of our memory is enhanced when the stimuli is particularly intense, right? That's when the amygdala really kicks into action, right? Now, for discussion, usually I tell my students to just read it up for yourself. You can actually read some interesting points that they pointed out there, particularly in discussion of why males compared to females, what the differences are in terms of the left and right side of amygdala. And they actually mentioned that a little bit in the discussion, and perhaps that explains, why the researchers chose to use females in this particular study. So do look at the discussion and read that up for yourself to get some background information and understand the study a bit better. Okay, let's look at some evaluation points, right? Strengths and weaknesses of this study. So first and foremost, it's an experimental design, right? Laboratory experiment, which is good, standardized environment. So materials and procedures all standardized. Everybody goes through the same thing. It's very reliable. It can be replicated. Those are all good. The items are presented in the same way. How many seconds? Remember, 2.88 seconds. And then the fixation cross, also in the same way. You've got the bite bar to prevent them from moving around too much. A lot of standardization, a lot of control. And also it's using a within subjects design, right? Remember, the within subjects design is important. Why? Because it reduces the individual differences. So that's good. It's called got high internal validity, right? Fewer confounding variables, right? What about the data? What can we say about the data? Well, the data collected is primarily objective, as you know, because it is quantitative, objective from the fMRI scans, using the voxels, using the average scores and everything. So that's good. It's objective. There's no researcher bias when it comes to interpreting the data. However, on a downside, and this has been, I think, noted in your textbook as well, that we don't fully understand the human brain. So it's difficult for us sometimes to make we can't really say with 100% certainty that this is what it is, right? Because there's always room for error. And as I mentioned earlier, right, studies have shown that if you put a dead fish in an fMRI machine, it will show you the brain scan results of a live human being, right? Which is obviously not true. So there's insufficient knowledge, right, of the physiological basis of the fMRI. Sometimes we can't confidently interpret the data necessarily to indicate neural activity, right? We have some level of confidence, but we can't be overly confident when it comes to the data. We're not entirely sure, right? There's a lot of things that we still don't fully understand, right? So we have to take these interpretations sometimes with a pinch of salt. Right? In terms of ethics, was this an ethical study? Well, first and foremost, as I mentioned earlier, there was no full informed consent. Why? Because the memory test was listed as an unexpected memory test, right? That's how the study has phrased it. Now, the study doesn't actually say that informed consent was obtained. If I remember correctly, I don't see the word informed consent there. However, we can safely assume that for most studies, if not all studies, informed consent is there in some form or another. It's either whether or not there's a deception attached to it. In this case, there is a bit of deception. They were not aware of the subsequent memory tests that came later. So that might cause some psychological distress, right? It's not so serious. I think it would be traumatic. The pictures were also very intense pictures, right? Negatively valence, very intense pictures. That might have also caused some people some distress, right? What if the person has a phobia of spiders and then there's a picture of a spider there, right? That may have caused some level of distress. So that's not good because it doesn't protect people from harm. Other things, I think if I remember reading somewhere online, I think I saw, or perhaps in the textbook, where there was a sentence that mentioned that the personnel operating the fMRI machine were fully trained and competent in all the safety and required procedures, and so that you could make an argument that minimized the harm, or that makes the experiment more valid because you used trained professionals in order to conduct the MRI, right? To conduct the fMRI scan, right? So that's good, reassures participants that everything is done in the right manner and make sure that they're taken care of. Okay. We can also talk about the validity of the study. What about the internal validity? Well, it controlled well for confounding variables, and so if it does that well, then the internal validity is much higher, right? We did this with the within subjects design, so that's good. It makes us more confident that the causal relationship is more definite, right? The IV is affecting the DV by removing all the confounding variables from within the study, right? They also use like the baseline scores and minus the activation scores minus the baseline scores. So that's good, right? They're trying to make sure that whatever pixels that they're looking at, whatever brain scans that they're looking at the final score is a accurate representation of brain activity without being affected by possible baseline measures, right? We can also talk about the sample, right? The sample was rather small, only 10 participants. So it's a small sample, not very generalizable, again, all female. So again, not generalizable to male. There's a gender bias. They were all right-handed, right? Perhaps left-handed people respond differently. We're not sure, right? So the sample is a bit, in terms of sample, I think I would say a lot more weaknesses there. The only strength that I could possibly argue with regards for the sample would be that women are more likely to express the emotional intensity, right? As we discussed earlier, that's why women were recruited. So perhaps on that side, the sample is beneficial in terms of the strength, is that by using women, you're likely to get more accurate results because women are more willing to share about their emotionally intense experiences, right? But it does lack a lot of generalizability. So that's an issue. Right, I usually give a memory test to my students. I ask them, basically I can ask you now, right, as well. Do you remember, what pictures do you remember I showed you in the beginning of my slide presentation, right? What were the pictures? Do you guys remember them? There were a few pictures. I had a handful of pictures. Try and think about them. What were the pictures you really remembered? I bet you probably remember the shark or the skydiving or the crying child. But do you remember the neutral pictures? What were the neutral pictures like? Do you remember the picture of just like white color sand? That was a neutral picture. I bet most of you probably forgot that if I'd asked you to remember it. But I bet most of you probably remember the things like the shark or the crying child, or even the skin with staples on it, right? So those were the emotionally intense pictures, right? Those definitely probably easy for you to remember. The neutral images, probably not so much, right? So once again, that's me. Hi, my name is Ross. I lecture psychology at Sunway University in Malaysia in the A-levels department. I'm pretty new to psychology in A-levels. I did my own psychology as a degree, but I never actually did A-levels, however. So this is pretty new for me, but I do my best. I hope you guys enjoy it. Please help me by liking, commenting, and subscribing. All those 3 options are completely free, and they do help my channel grow and go a long way. So thank you so much, and do share these videos with your friends. If you want to, if you want to contribute to me financially, that's also very much welcome. Drop me an email. Just read the section below in the about section of the video, and you can find more details there. I do have a Patreon account, so you can support me there as well if you want. Thank you very much, everybody. I hope this helped you get a very simplified overview of the Canli et al. Study. It's got a lot of jargon, a lot of details and all that. I try to keep things simple so that people don't get too overwhelmed. Right? So I hope this video has helped you. Thank you very much, and have a great day.